All right, welcome. It's almost reading week. Yay. So you'll have some, well, knowing that you're in engineering, probably it will kind of suck, but hey, you won't have to go to campus, so that's something. So today should be mostly review, so we're going to go over another scheduling question just so we refresh ourselves before we have a reading week and quizzes and all that stuff. And to go over one of the exam questions that were there previously, just so you have something to base it off. So let's go ahead and take a look. So we'll explore, we kind of touched on it before. We talked about, hey, we could have priority scheduling, but we could also have dynamic priority scheduling, where our algorithm can control the priority dynamically, change it so that you have, your IO-bound processes get CPU when they need it, and then your CPU-bound processes get to execute for a long amount of time, so you have better throughput, and try and balance the best of both worlds. And this is one heuristic to do so that you kind of find the IO versus CPU-bound processes. So it may also be called feedback scheduling because we are keeping track of how long things execute for and using that to dynamically change the priority and keep track of what process we should run and where, because that's scheduling. So we let the algorithm manage the priorities. So we're going to use set time slices, and then we're going to measure CPU usage, and then within a time slice there's going to be timer interrupts. So there's going to be many timer interrupts within a time slice where we could change processes if we want to, but we that don't use the time slice. So those are processes that just need the CPU for a little bit and then pretty much get blocked or go to sleep. So you want to have good response time for that. So whenever they're ready, you essentially want to. So in this case, decrease priority means make it less important. So I want the CPU-bound ones to be less important. I want the IO-bound ones to be more important so that they're scheduled and you get good response time. But confusingly, we're going to use the opposite numbers. So higher priority will mean a lower number, which is kind of what the Linux kernel does. So we'll see that. So like we just said, we're going to pick the lowest number as the highest priority in this case. So how it's going to work is each process gets assigned a priority when they're started, say Pn, where n is the process ID number. And then we're going to pick the lowest priority to schedule. And then if that process decides to yield or block or whatever and gives it up, we pick the next process in our queue based off our priority order, and we can break ties with a rival order. And then if a lower priority number becomes ready, we schedule that. So if there's a tie where something of the same priority is already running, we won't bother switching to it. But if a higher priority or lower number comes in, we'll schedule that immediately. So we're going to record how much time each process executes for in its time slice. So we'll have timer interrupts. So we're essentially just counting the number of timer interrupts that each process is executing for. And there'll be more of that than in the time slice. So you'll essentially get to play with these numbers, but at the end of the time slice, you'll update the priority. Yep. Or we kind of talked about before, we'd have multiple queues for each one, or we could have one global queue, or we could kind of do a mixture of both, where we have that work stealing thing. So we talked about it, but you wouldn't have to like write out a full-blown answer about that because it would just take too long. So at the end of each time slice, so we're going to update the priority of each thread with we're going to half its current priority and then add however many timer interrupts it executed for, and then we're going to reset the value of C for all the processes. So the idea here is to have the highest priority eventually. So that is our way to be nice and fair, and you can do all sorts of different heuristics, but this is probably the simplest one to understand. All right. So the question on the midterm that they went over is so it was missing a bunch of information where you had to make your own assumptions. So one assumption you could make is that, hey, the initial priority of all the processes is 0 seconds, and each time, so within a time slice, there's going to be 10 timer interrupts that you have to keep track of and that you have to make scheduling decisions for. So the question asks, what's the schedule that would be generated? So if I assume that they're all ready to execute, and I get them in arrival X, Y, A, B, what should execute first? X. So X was the first one there. They all have the same priority in this. So I would execute X. And based off the question, it just executes for 0.1 second. So it only executes for one timer interrupt. And then it blocks for 0.5 seconds. So it would only execute for one timer interrupt. And then it blocks. So we can't schedule it anymore. So we have to pick a new process. So what should we pick next? Y. So we pick Y because it's the next one in arrival order. It executes for 0.1 seconds, goes to sleep. Yep.
So it executes, so each of these blocks is 1 second, right?
Each of these blocks is 0.1. So each of the blocks is a timer interrupt where we could context switch.
Okay, so then we don't care about the 0.5 seconds. So 0.5 seconds is like, it has to wait at minimum 0.5 before it can come back in.
So the 0.5 seconds will come into play once, like it will add it back to the ready queue and we can schedule it again. So it will come back into play, but for now it just executes for 0.1 seconds and then it will take 0.5 seconds. So whenever we start executing timer interrupt 6 at like 0.6 seconds, then process Y or X will be ready again. So that's what we'll do. So in this case, time 6 here, that's when X becomes ready. But we would, after we execute process Y, it goes to sleep. We have to pick between A and B. So we would pick process A. So it executes, and whenever X becomes ready, we don't switch to X because it has the same priority of what is currently executing. So we just keep on merrily executing process A until the end of the time slice. And each time slice in this case, based off the question, is 10 of the timer interrupts. So everyone okay with that? As much as we can be. Yeah. At each time slice, and at each time slice it recomputes the priorities. So we have to make a decision at the end of each time slice. Okay. Yep.
So you said that when it was like A was executing and then X becomes ready in the middle and then take over?
Yes. Yeah. So if X, so we'll see an example where X, all we have to do is change the initial priority and we'll have that scenario. So we'll see an example after this. So this is the first one if we assume everything is 0. So yeah, X became ready at the end of, or at the beginning of time slice 6, but we didn't switch to it because everything was a nice big tie. And then Y became ready at 7, but we didn't switch to it because, again, everything has the same priority at that point. So A would stay there until the end of the time slice, which is 10 of these boxes. So every 10 boxes or every 10 timer interrupts, we get to recompute the priorities, and then that would change our scheduling decision. Yep.
Also, like, all the processes will just run from beginning of time. So if they start executing at the beginning of a time slot, it will just keep executing until the end unless it blocks or a new higher
Priority, yeah.
comes in.
Yep. Yeah, so a process will go in, it will start executing for all, it will try and execute until the end of the time slice, unless something of higher priority is now runnable, and then you would switch. So in this case, at T10, do I schedule based off these priorities? So the version of it would be if processes A and B have a priority of 6, and then X and Y have a priority of 0. Or they're blocked. So where are we going to schedule? A. So there's a tie between A and B. A came first, so we'll just